Good morning and good afternoon, everyone, depending on where you're joining us. My name is Georgia Marchant and I am PR and social media lead at Fluke Reliability, which is home to eMaint and Proof Technic. We've got a really special webinar for you today. Our speaker is Taylor Shepherd, who's a field application specialist at Fluke Reliability, and he's going to talk to us about vibration analysis in an evolving condition monitoring environment. First, we still have a couple of people logging on, so I'm just going to give them a minute and we'll get underway. But you will see a poll popping up on your screen. If I can just invite you to vote what you think of the poll before we sort of introduce Taylor and begin the webinar. Awesome. To see a few other people joining. Cool, I think we're ready to go and we can let anybody else join on. So thank you so much for joining us for today's webinar. As I said before, it's called Vibration Analysis in an Evolving Condition Monitoring Environment. And our speaker today is Taylor Shepherd. Before I formally introduce Taylor, I'll just cover a couple of housekeeping questions. So today's webinar is being recorded and we will share a link with you after the event. You'll also be able to find it on Fluke Reliability's YouTube channel. So if you do want to revisit the content or share it with someone, you can. As always, we also invite your comments and questions. So you'll see a Q&A chat box on your screen. If you think of a question at all during the speaker's presentation, then please just type it in there and we will have time at the end for Q&A. As I mentioned, today's presenter is Taylor Shepherd. Taylor is a Cat 3 vibration analysis with over 10 years experience in vibration. And Taylor, thank you so much for being here. With that, I will hand over to you for today's talk.
Okay, great. Hey, my name is Taylor Shepherd. I appreciate you guys all coming and hearing me today. This is a Chinook helicopter. It's being forced into a ground resonance condition. With the evolution of condition monitoring technologies and the advancement of AI, the spread of wireless technology, which sends the vibration data offsite for analysis, the traditional vibration analyst may feel like this is an analogy for their career. Maintenance managers are seeing the benefit of these new technologies and may find themselves wondering, do we still need on-site condition monitoring personnel? Today, I'm here to discuss vibration analysis in the evolving condition monitoring environment and the changing role of the traditional analyst. As we said previously, my name is Taylor Shepherd. I'm a Cat 3 vibration analyst. A little bit about myself. In 2008 or so, I stopped doing the dumb stuff and got a job in industrial manufacturing. Took a few welding courses at the Community College of Denver and worked for the Boilermakers out of Denver. They didn't work me enough to keep me busy, so in 2012, I started at the Climax molybdenum mine as an entry-level mill maintainer. I worked there for several years, working up to a mill diagnostic mechanic in the molybdenum concentrator, where I was showing a pretty strong aptitude for diagnostics and troubleshooting. So somebody offered me a job for reliability-centered maintenance, and I made my way up to the senior reliability-centered maintenance tech there. 2020, COVID came along, messed up everything. So I took a position with the Cripple Creek and Victor gold mine. But that was kind of short-lived. The Cripple Creek and Victor was kind of end of life with their mill. So 2021, we moved to the Oregon coast. There, I got a job working in a paper mill, working as a reliability-centered maintenance tech. Working in paper mills isn't fun. So when 2022, when Fluke come a-courtin', I took their position as a field application specialist, and here we are today. Condition monitoring is the process of monitoring a parameter or condition in machinery in order to identify a significant change that is indicative of a developing fault. Why? Well, because things like this. This is a planetary gearbox, or was a planetary gearbox, where the sun and planetary either ingested something or something went wrong inside the box and it chewed on it for a little while. Ended up with catastrophic damage. Here, we're seeing where a coupling failed and due to the imbalance caused by that coupling failure, due to the imbalance caused by that coupling failure, it eventually tore up the bearings in the motor, causing secondary damages. In this case, we're looking at a gearbox and bearing. If I was to guess, this is probably coming out of the output shaft of a gearbox. And I say that because when I was working at the Cripple Creek and Victor Gold Mine, we had a similar thing happen where people may not have considered the thermal growth coefficient. And when they mounted the gearbox, they did not take into consideration that the gearbox was going to grow more than the mill did, causing an overload condition on the output shaft, which ended up spalling a gear, taking out the bearing, something very similar to this. In this slide, we're looking at the obligatory P to F curve. Can't talk about condition monitoring for very long before somebody shows you this. This demonstrates the progression from precision state to failure state. Once equipment enters the failure state curve, there's a fairly well documented progression of failure indicators. Early stage indicators include things like oil analysis and ultrasound. Oil analysis tracks wear particles and additive depletion. It's an excellent maintenance practice where degrading results are an early indicator of problems. Ultrasound can detect lubrication issues and metal on metal contact, providing insight as to early evidence of bearing faults, but it can result in premature repairs, and that shortens the lifespan of the equipment. In the Goldilocks zone, we have vibration analysis. Vibration analysis can inform us of a wide range of issues months in advance. This allows analysts to track the severity of faults and determine the best way to respond to the issue. In addition to traditional vibration analysis, this can include tools like motion amplification and modal analysis. The comprehensive nature of vibration analysis provides valuable tools in identifying the root cause, identifying the root cause of mechanical faults. Just past vibration analysis, we have infrared thermography. Infrared thermography of bearings detects the later stages of bearing wear, where the bearings start to heat up. And unless you are running those bearings in a run to failure application, that's too late. However, thermography can provide great insights as to the early detection of electrical transmission faults, and simplified thermography tools like IR thermometers are great tools in the hands of your operators doing screening during their daily maintenance checks. In the ideal world, perfect maintenance practice would be good for everyone. It would increase uptime, it would lower maintenance costs, it would allow planners to plan the work. It would increase safety, it would boost peace of mind, and it would improve your morale. That's not what happens in the real world. In the real world, there are three general types of maintenance practices. Failure-based or reactive maintenance results in unplanned downtime, production losses, and higher maintenance costs. When equipment fails, it often results in cascade failures due to the sudden interruption of your process. Next, we have interval-based or preventive maintenance. And this can result in the overhaul of fault-free machines. This uses the theory of, I know it always fails at about 6 months, so we'll replace it at 4.5 months. And you'll still find yourself having failures of otherwise good machines. Condition-based or predictive maintenance is sometimes referred to as reliability-centered maintenance. Using predictive maintenance, the appropriate time frame for repairs is determined by the machine's actual condition. Those repairs are done using precision techniques such as laser shaft alignment, and after the work is completed, it's verified for accuracy. This is a segue. Vibration analysis is a process for measuring vibration levels and frequencies of machinery, and then using that information to analyze how healthy the machines and their components are, for the purpose of predicting failures in industrial equipment and increasing plant reliability. Vibration analysts are skilled technicians who are generally fairly hard to come by and expensive to train. Oftentimes, these technicians are taken from the top tier of your skilled maintenance tradespeople, which may leave you a void that's difficult to backfill. Route-based vibration data collection has long been the bread and butter of a plant reliability program. This is a time-consuming undertaking, both in the collection and the review of that data. Using a handheld vibration data collector, an analyst will walk the plant, moving from machine to machine to machine, collecting the data. And while it's time-consuming, it allows analysts to not only collect vibration data, but also to observe the equipment for things like overall plant condition, leaks and loose fasteners, tripping belts, and misaligned conveyors. It also allows them to observe things like general plant condition, things like safety and cleanliness. When I was a vibration analyst working the floor, easily a third of my work requests were for things like safety repairs. The analyst then reviews the data that they've collected and makes recommendations for the repairs by writing work requests. Online vibration data collection systems collect data across many measurement points and sends that information to a server-based database. It results in vast quantities of very repeatable data, which still must be reviewed by vibration analysts. The system's not set it and forget it. It requires a fair amount of maintenance to make sure it stays in good condition, making sure that your accelerometers stay attached or your cables are not being damaged by maintenance practices or operational upsets. Online data collection systems can be costly, but they deliver really high quality data. Once you have all this data, absolutely the most time-consuming aspect of vibration analysis is the data review. Whether it be route-based data, online data, or a combination of the two, there can be an immense amount of data to be reviewed. This means that the analyst must spend a lot of time in the seat, examining all the squiggly lines, trying to locate a very small needle in a very large haystack. The database has to have some maintenance itself. Database management is required to ensure that the database stays accurate and manageable. An accurate database results in efficient data analysis. You need to do things like update your machine changes, whether they be from maintenance or modification, or managing your alarms, whether you're managing your band alarms or you put in some enveloped alarms. And you need to manage your alarms to incorporate operational changes. And then, being as how so much data is collected, you must manage your data storage parameters. If you don't have a plan in place to do that, eventually you will run out of space. And the goal is to use all this vibration analysis to detect failures in their incipient phase, to make the call to replace the bearing long before it fails, to give the planners a chance to schedule the repairs and order the parts, to allow the operators to shut down the equipment safely and correctly without upsetting the process, and to give the maintainers the opportunity to conduct repairs during their scheduled work period. That's not always the case. Here we have an example of a catastrophic failure where the bearing failed. The motor continued to run. The driven side of this machine carried the shaft long enough that the friction from the failed bearing began to heat the shaft. Eventually, the coupling failed and allowed the rotor and stator to come into contact. That's when the smoke got out, and you're not going to fix that. So when I was brand new into vibration analysis, I had dreams of all the different aspects of the reliability field that would open up to me. And I did dabble in tribology, even got my machinery lubrication technician one. I made a few findings with some NDT equipment. I've aligned a few pulp refiners, and I've balanced a fan or two. Heck, I've even had the opportunity to participate in a root cause failure analysis. But I was always busy with vibration analysis, so I never had the opportunity to really shine in those areas. Every day in the news, we hear about AI and how it's going to make the world a better place. Soon, AI will be in every aspect of our lives, and condition monitoring is no different. When that happens, our robotic overlords will have taken over. Three challenges facing today's predictive maintenance leaders are things like how to grow a reliability program. There's no time to implement a comprehensive reliability program. When we do, how do we make the best decisions? We don't have time to collect all the necessary routes, much less analyze the data and generate the reports. You got to figure out which assets you want to monitor. How do we monitor all the critical assets when we still have to allocate resources needed for planned maintenance, break-in repairs, and emergencies? And there's always that fourth kind of unspoken challenge, which is culture. Maintainers and managers alike may resist the implementation of a reliability program because it doesn't seem broken to me. Today's maintenance tools are the most advanced. The software is most powerful, and trainings have never been more available. Whether you're taking those trainings online, in person, or doing a hybrid of the two, the problem has always been time and resources. The healthcare industry also deals with limited resources. They follow a tiered approach to handle this. You go into the doctor and generally you see a nurse practitioner. Most of those nurse practitioners can handle many of the screening and wellness checks tasks without involving your doctor. When an issue exceeds that nurse's scope of training and experience, your family doctor comes in and can probably diagnose most common problems and provide a treatment plan. For problems beyond the family doctor's scope, you may be referred to a specialist with advanced training and experience. Similarly, in condition monitoring, we can use condition-based screening to help reduce predictive maintenance workloads. If we screen our equipment, we don't waste our resources analyzing healthy machines. That gives us more time to diagnose, to see what is really going on with an asset, using advanced analytical tools for a deeper look. And eventually, finally, we have to analyze. We utilize our expert analysts to determine the nature of machinery faults and to help with root cause analysis on critical assets. Wireless data is the up-and-coming technology. This technology has made a huge impact in the data collection of many previously unmonitored machines in a facility. In many wireless data applications, we hear the catchphrase AI. I encourage you to be skeptical, as this is a developing technology. Vibration analysis is nuanced, and it's more than just observing the data and making calls based on that data alone. This may be best utilized as a screening tool. One of the shortcomings that people find with a wireless data collection system is the data collecting sensor is subject to physical disruption. The sensor itself may find itself to be the target of a prankster. Oftentimes, you walking around a plant that has a wireless system installed, you may find wireless sensors stuck to the back of forklifts. The screening that was traditionally done during route-based data collection can now be done by wireless sensors, so that analyst doesn't have to go from machine to machine to machine. And this allows for many, if not all of your assets to be screened with reliable, repeatable results, so long as the sensors are in place. These sensors report to smart software that makes it easy to set and adjust alarms, reducing the amount of time that is spent reviewing data on machines without faults. Thus, it reduces the amount of time that your vibration analyst spends collecting and reviewing route-based data. Online data collection systems are generally the most accurate data collected. They create an immense amount of data, and it can quickly become overwhelming. Online data collection systems are costly, but they deliver very high quality data. In this picture, we see the tending side of a paper machine dryer, and this is where the operators spend most of their time. The motors and the gear sides are on the other side. They're on the drive side. And vibration data is largely collected from the drive side, which is a terrible place to have to physically collect data. It's very hot, and with exposed dryer cans and rotating shafts, it can be a little dangerous. So that makes it the optimal application for an online condition monitoring system. Online condition monitoring systems can utilize virtual servers, and this allows the data to be viewed remotely, which in turn allows for remote condition monitoring. Remote condition monitoring services allow off-site personnel to review vibration data. Due to the nuanced nature of vibration analysis, it's helpful for analysts to have a familiarity with your process. So, remote condition monitoring teams review the data, make recommendations to site personnel who then inspect the equipment. It may seem a little complicated, but in truth, it empowers your site personnel to concentrate on the equipment that has progressed into a failure state. And it reduces the amount of time your vibration analysts spend reviewing data on fault-free machines. So, armed with the recommendations of remote condition monitoring and wireless screening tools, the on-site vibration analysts take hand data of equipment with advanced vibration data, advanced vibration data collectors. These on-site personnel observe the equipment, review the data, and verify the failure state. They then make the recommendations for repair for work requests into your CMMS, or computerized maintenance management system. Some of these online and remote condition monitoring systems report directly to your CMMS. Since this equipment has been pre-screened and already shows some evidence of potential faults, your site vibration analysts are able to focus on other aspects of condition monitoring. But what if you're just getting started? You may be working on a shoestring budget, and this may be where remote condition monitoring services can provide a lot of return on investment. Often, a new reliability program kind of stalls out. Also, as a plant reliability team is generally very small, sometimes just one person, the installation of wired systems, the building of route databases, and the deployment of wireless sensors is time consuming. The people who write you the checks want to see some return on investment. Without that, they're unlikely to look favorably on your reliability program growth. Or worse, you may have a conspicuous failure that may have been prevented by a new reliability program. And without that credibility, your program is sunk before it gets underway. So I advise you to scale your condition-based maintenance program. Be vocal about your successes and always look for ways to grow your program. A best practice solution is to start with a pilot program. Show success on machines in one area of your plant and then expand across the entire organization. And don't start necessarily with your most complex machines. Start with your most common machines, or maybe your most problematic. As time progresses and you collect more data, review which machines may need more or less attention and data collected. And as condition-based maintenance technologies are evolving, be aware of changes in the capacity that can positively benefit your organization. Most of us have probably seen the video of the Tacoma Narrows Bridge failure, and hopefully all of us do laundry. The Tacoma Narrows Bridge is a spectacular but somewhat inaccurate example of mechanical resonance. July 1st, 1940, the bridge opened, and on the offset, when wind speeds reached sustained speed of 35 miles an hour, the bridge experienced resonance due to aerostatic flutter, as opposed to true mechanical resonance. The bridge eventually collapsed, November 7th, 1940, when the winds reached 40 miles an hour. A more accurate example of resonance is your washing machine. You may have noticed as your washer goes into its spin cycle, it goes through a period of increased vibration. That goes away either as it goes faster or as it goes slower. That increased period of vibration is the machine passing through one of its resonant frequencies. Resonant vibration in mechanical structures such as pumps, turbines, and motors occurs when a natural frequency is at or close to the forcing frequency, such as rotor speed. In order to avoid running the equipment at potentially destructive resonant frequencies, vibration analysts using advanced analyzers conduct resonance tests. Knowing knowing the natural resonant frequency allows the analyst to make recommendations and avoid operating the machine at a speed plus or minus 10% of the resonant frequency. Run up and coast down tests measure and detect resonant frequencies in machines that are in operation. And then bump tests can detect resonant frequencies in machine components like your fan wheels. These expert vibration analysis tools generally also include a balancing function. It allows a skilled vibration analyst to balance rotors. It's a bit of an art form. They provide for single plane and dual plane balancing, overhung and center hung rotors. One of the tricks to successfully achieving a balance on rotating equipment is to remember that it is vital to rule out every other source of fault energy. Looseness, coupling issues, bearing issues, alignment, all of it, before you attempt your balance. So we discussed what's changing and improving in the world of vibration analysis, and now let's talk a little bit about what happens after you've collected the data. First, you need to do your screening, and this may include enabling your operators, making their daily rounds more productive, maybe giving them a little bit of training or simplified tools like those IR thermometers that I mentioned earlier. You're going to go through the alarms that your screening has produced, and you're going to verify your potential faults. Then your vibration analyst goes and collects full spectrum data, and reviews the oil sample data. Maybe do some non-destructive testing, and eventually, once you have identified that something truly is in fault condition, you're going to write some work requests. Those work requests go to the planner. The planner does their best to schedule the work appropriately, which allows your operators to shut down the plant safely. One of the things about a planner's job is they have to verify the availability of parts. With everybody working towards lean manufacturing, parts have lead times. And if you do have spares on hand, you have to verify those spares, because sometimes in the middle of the night, they might be taken for a break-in maintenance. And then if you don't maintain your spares and your bearings sit on the shelf for too long, or your motors stay in the warehouse for too long, you may find yourselves with bearing fault conditions developing from conditions like false Bernelling. Once you have planned your work, got everything shut down, you're going to do the maintenance. You're going to install it. You're going to do it safely, you're going to do it efficiently, and you're going to do it using precision techniques. When it's all done, it needs to be validated. You're going to collect your post-repair data and update your databases. And last but not least, you have to determine why you're experiencing these failures. So, what is precision maintenance? Precision maintenance is an approach to plant maintenance in which tasks are performed consistently, accurately, and with a high level of precision. This is accomplished by trained maintenance professionals using tools such as standard operating procedures, SOPs, absolutely a tool. Standardized maintenance training. It is always helpful to have everybody trained the exact same way and not have to rely on the tribal maintenance of your team. You're going to provide quality precision hand tools and modern electronic tools to make sure that this work is being completed in a precision manner. Precision hand tools include things like a calibrated straight edge or a dial indicator. That straight edge is going to measure flatness. Dial indicators measure runout. Historically, maintainers use straight edges with feeler gauges or reverse dial indicators to perform alignments with varying degrees of success. Calipers and micrometers measure the inside or outside dimension to make sure that your shafts and your bearings are the size that you believe that they are, and it ensures the fitment of the components. Your torque wrench, well, obviously it measures tightness, and your machinist level will measure your true level. It's been determined that it has been determined that misalignment of industrial equipment is responsible for up to half of machinery failures. Misalignment can be diagnosed using vibration analysis, which in turn allows analysts to make recommendations for corrective action. Not so long ago, I was out on a customer visit with one of our territory reps, where we were told by a customer that they were conducting alignment using straight edges and beer cans for shims, with varying degrees of success, I suspect. Laser shaft alignment tools can measure shaft alignment, bore alignment, and thermal growth, and they are by far the most accurate commonly available alignment tool. They have maintenance personnel friendly interfaces, allowing for quick and accurate alignments as part of the work process. And these top tier tools can align things like offset cardan shafts and shafts with multiple couplings, shafts where one side of the uncoupled equipment can't be turned. And they have the ability to measure and correct for thermal growth. Roll alignment tools can measure roll parallelism and as the work is completed, allowing for real-time verification and adjustments. Utilizing proven technologies and experienced teams of personnel, these tools can measure a large number, if not all, the rolls in a plant during a maintenance outage, and they provide very fast results. Next is this. This is easily the cause for the most strife between your maintenance team and your reliability team. When the work is complete, one of the jobs of the reliability team is to do the precision maintenance verification. And this serves multiple purposes, not the least of which is to gather baseline data on the completed work. It also serves to verify the work was done accurately and to precision standards. Unfortunately, the point where the strife occurs is when the maintainers and the the point where the strife occurs is because the maintainers look at this as a quality check of their work. Here, we see a brand new black liquor pump. The previous pump had failed, and when the maintainers installed the new one, they signed it off as completed. This included the alignment of motor to pump. The pump that they installed had a difference in overall height from original to replacement, therefore required shimming to alleviate the pipe strain, which is fairly common in older plants. But what's wrong here, aside from reusing shims? Well, why are the shims loose? Well, there's no washer on there. Without the thick structural washer, the bolt bottomed out in the tapped hole. The torque wrench clicked, and with the weight of the pump on the shims, the pump held in place by the piping, nothing seemed to be loose until the follow-up precision maintenance checks. Here we have our second pull. So, once the maintenance is complete, root cause failure analysis takes a deeper look into the underlying causes for failure and determines a path of action to prevent the exact same failure from happening again. And many parameters are considered. The vibration data, the historic data, the analyst observations, resonance inspections, all of it. With root cause failure analysis, you examine your operational parameters. Has something changed in the way you're running the thing? Look at your maintenance activities. Did something get damaged? Was something perhaps misaligned during installation? Look at all your maintenance activities and see what may have changed that's causing these failures. And then your overall plant condition. And while plant condition includes things like housekeeping, it also includes things like, has your plant settled? In some places, you find plants along waterways, and those waterways sometimes erode underneath the plant, allowing for machines that were installed decades ago to not be in the same general alignment as they once were. You may find it helpful to involve personnel from outside your group, your site, maybe even outside your organization, to provide an unbiased look into the root cause of your failures. As apt as it may be, this is not the forlorn cry of your maintenance manager pounding their head against their desk. 5 whys is an interrogative technique used to explore cause and effect relationships underlying a particular problem. The primary goal of the technique is to determine the root cause and effect of the defect or problem by repeating the question why at least 5 times. Generally, the answer to the 5th why should reveal the root cause of the problem. This technique was described by Taiichi Ohno at the Toyota Motor Corporation, and it's a good tool to use whenever you're seeing repeated failures. So, modern technology is changing the way that vibration analysis data is collected and utilized. What does this mean for personnel previously buried by route-based data collection and review? It means that there's less time spent collecting the data on mostly good machinery, which means that there's more time for diagnostics on equipment that has been pre-screened and actually has a potential fault. There's more time to invest in alternate reliability technologies such as alignment, balancing, oil analysis, non-destructive testing, more time to concentrate on your database management, more time for your hardware maintenance, whether it be online system upkeep, wireless sensor maintenance, and more time to conduct your precision maintenance verifications. And then at the end, there's more time to address the root cause of failures. When you're discussing your plant reliability around your facility, you may have heard grumblings like, back in my daddy's day, well, back then you had no guarantee you'd go home with all your fingers. There was a lack of concern about what went into our rivers and landfills. Towns literally lived and died with their industrial sites. Run to failure was an acceptable maintenance practice, and running full tilt was the only way to make goals. And in the end, there was actually a line of people at the gate waiting for that open position. The modern reliable plant needs to focus on more than just the production of their given product. Equipment reliability is at the heart of these goals, and vibration analysis is still at the core of a reliability program. That's all I got.
Thanks so much, Taylor. Cool. So we've got a couple of questions here, but thank you so much for your presentation. And I just wanted to remind everyone, as there's been a few questions in the chat box, today's webinar was recorded, so we will be able to post that on the Fluke Reliability YouTube channel, and you'll be able to access it there. But we'll also send a link out to everyone who attended as well. We've got a couple of questions here, but if you haven't yet submitted a question, please just pop into the Q&A box now and submit it in there, and we will ask Taylor. So Taylor, the first question is, our facility has been looking into getting vibration analysis, but we don't know where to start. What do you recommend?
That's a great question. So when you're first getting into reliability-centered maintenance, you may see the complexity or the cost as a little daunting. And so the best way to kind of break into it is to explore your options and determine what your critical equipment is, what your less than critical equipment is, and decide for yourselves, what you want to monitor first. It may not be in your best interests to go after your most complex thing first, but instead, perhaps your most common or what you're seeing the most failures in. So start with the tiered approach. Start small and work your way up.
Brilliant. We've got another one here that says, how do you ensure that all key components are addressed on a machine under predictive maintenance?
You need to make sure that you do a survey of the machine, depending on whether you're talking about a complex machine or a simple machine. And I say a simple machine, it's fairly straightforward. So a simple machine being like a pump motor combination or a motor fan combination. So you want to make sure that you know what your horsepower is, what bearings you have in there, things like that, and make sure that you keep that accurate and updated in your database. If you're looking at a more complex machine, you'll want to make sure that you're taking data at the right point. Data can be skewed by taking data in an area where you are seeing multiple components with the same sensor. So you want to do a survey and make sure that you're installing your system where it is appropriate and you're installing the right size system, not underselling it, not trying to get by with too lean of a monitoring program, and monitor completely and thoroughly.
Cool. And then someone's put in here, vibration analysis, can it really be applied in an AI process?
So vibration analysis has long been, the subject of machine learning. And so there are a lot of machine learning algorithms out there that can detect alarms, detect changes and things like that. And those are watching your overalls. For AI, it is a developing technology. And I'm sure that when AI has reached its point where it's helping us and not being our robotic overlords, that it will reach the point where it can do diagnostics. At this point, be skeptical of it. If you have somebody saying that your data has been reviewed with AI, it's probably been reviewed with machine learning and standardized alarms.
Brilliant. And then we've got one that says, how would you suggest to start an RCM program, and what are some strong points to convince management?
So reliability centered maintenance is deep and it's nuanced. And so the best way to start is to do a site survey. Determine, again, what is your critical equipment and your less than critical, and determine where you want to start. And depending on whether you wanted to start with a big program which takes a big budgetary ask, or whether you wanted to start with something smaller and show a couple of wins straight away, it is kind of up to you. But if you have skepticism inside of your plant about the value of reliability centered maintenance, try to target for wins you can get. So you start monitoring common failures and do it with perhaps wireless technology, and that will allow you to get some early wins early on. It'll help you learn the value of reliability centered maintenance, not just for your plant and your plant operation, but it'll also help somebody who may not be very experienced ease into it. If you use remote condition monitoring services, these provide expert on demand services that can help you learn your way into a comprehensive program.
Awesome. And then we've got another one here that says, we have a one channel Vibexpert 2. Can we use that to balance fans?
Well, as it stands, you would not be able to. But I can't speak for other branded tools, but I can tell you that the Vibexpert 2 is upgradable. And so yeah, contact your local salesperson and see if they won't be able to help you upgrade. And you may find that there are other tools out there that you're interested in.
Awesome. How do you weed out false alarms?
Well, when you're using remote condition monitoring, that's where the nuance comes in. So you have false alarms where you have machines running right next to each other, and you're having some transient vibration and things like that. So you have to weed out false alarms by going and doing the legwork. You go and you learn what these these frequencies are, and you may find that things that seem like a false alarm are transient faults, so instead of transient vibration. So it's something that's happening in that machine, but it's not happening at all times during its production process. So keep an eye on it, and eventually you'll figure out which ones are real and which ones aren't. That's why vibration analysis is nuanced.
Cool. Do you recommend vibration analysis for reciprocant compressors?
So it has value, but due to the nature of reciprocating compressors, there's a lot of noise going on. And so what you'll want to do is, when you're doing vibration analysis on reciprocating compressors, is pay close attention to your overalls. If you're seeing an increase in your overall energies, that is indicative of something changing. Once you know that something is changing, that'll allow you to do a little bit of a deeper dive, and hopefully you'll be able to find the specific thing that is beginning to fail.
Awesome. And then someone's put here, in the case that you don't have software to analyze your data and you're sort of manually collecting the data, what's the best way to analyze it?
So I'm not sure about the question, but I'll take a poke at it anyways. So if you don't have the software, that probably means that you're using a simplified vibration data collection tool. And you may find yourself needing to make yourself up a spreadsheet where you are recording your overall data, because those simplified tools generally take overalls, and you use that spreadsheet to track your overalls. And if that's not working for you, I would say maybe take a look at some of these wireless technologies. These are, I hesitate to use entry level, being as how they are expert tools, but they allow people that may not have the most vibration analysis experience to send their data off where it goes through the machine learning and gets alarms applied to it, and can help you determine what your faults are without investing a lot of money into a new program.
Brilliant. And then we've got, what are your thoughts on having vibration as a parameter that is being continuously monitored, similar to how temperature is always monitored?
So when you are continuously monitoring vibration, you are generating a vast amount of data. So what our solution for this is we set vibration data collection parameters. So say you're using an online vibration data collection tool. That vibration data collection tool can collect, in some cases, just as fast as it can, but that doesn't necessarily mean it needs to save that data. By setting alarms to those overalls, once it surpasses an alarm, it'll collect full spectrum data then. And then at a set interval, whether it be 1 minute, 1 day, 1 hour, depending on what your data storage parameters are, it'll collect full spectrum data across all the channels.
Brilliant. And then another one that came in said, what would be the best tool for analyzing vibration of a non-rotating asset, i.e. a HV electrical transformer?
Boy, I wish I knew the answer to that. But
good question. Email in and we'll be able to find somebody else that can answer that one. And then someone said, having trouble convincing maintenance techs that bearings are in failure mode according to the data that they're used to.
So this is the age-old problem that reliability people face with maintenance people. And maintenance people, like, it doesn't seem broken to me. What has always worked for me in the past, well, I won't say always, what has worked well for me in the past is when I have made a call on a bearing and the maintainers pull it out, it helps if I'm there to lend any assistance that I can. And that helps my credibility with them. And then once it's pulled out, clean up that bearing and show it to them. And have a look at it yourself first. Make sure that the fault is visible. Sometimes you may find that you've made a bearing call and the fault is a subsurface anomaly, which will result in nothing being visible, which is not great for your credibility with the maintainers. But when you do find one, and most of the time you find one that has a visible fault, show that to them. Show them what they're replacing, and have a conversation about you're trying to replace the bearing when the bearing fails rather than replace the shaft, or excuse me, replace the bearing before the bearing fails instead of replacing the shaft after the bearing fails. Kind of roundabout answer there, but I apologize.
No, that's good. And then if we have a wireless condition monitoring system, do we still need an on-site analyst?
So yes and no. Wireless and remote condition monitoring can detect failures in the vibration data, right? One of the things that they can't do is they can't go out there and actually observe the machine condition. So while you don't necessarily need to have an on-site vibration analyst, when you get recommendations from your wireless system or from your remote condition monitoring, somebody should go out and make sure that that's not something like a soft foot condition where a bolt has come loose and the shims have come free, or take their strobe out and have a look at the strobe and have a look at the coupling and make sure that the coupling is still in good shape. So no, you don't necessarily need an on-site vibration analyst, but you do need to verify the data that is coming into you.
Awesome. And then just one last question, because I know we've hounded you with a lot of questions here, Taylor. Thank you so much for answering them. Vibration analysis, vibration analysis in any woodworking manufacturing machine. What is the tolerance or monitoring in percentage to determine the machine subject for maintenance and repair? Sorry, it cut half of it off.
So this is a question that doesn't have an easy answer. To determine, where your vibration tolerances are is based on your machine speed. It's based on your bearings. It's just, on its loading, on things like that. So there's no easy answer for that. What you do is when you start your vibration analysis program, you collect data, and you collect data in what you believe to be a fault-free condition. So we'll call that your baseline data. Once you've collected your baseline data, you can go through and you can set your alarms. Generally at the outset, you want to set your alarms to the ISO standards. And ISO standards, if I'm not mistaken, alert is 100% over baseline and alarm is 50% over alert. That's a pretty wide range, but it covers most machines. That'll allow, but when you're setting your alarms, make sure that you're putting in your machine speed, your bearing information if you have it, and any other pertinent data that you may have.
Cool. Okay, so thank you so much, Taylor, for sharing your insight and expertise there. I don't know if there's any sort of comments that you want to make in closing there, Taylor.
Sure. If you could tell me what the results of the polls were, and maybe we can see where everybody kind of landed on this.
Good question. Robin, can you help?
Yes, yeah. I can provide the results of the first poll. Unfortunately, I got kicked out and didn't get to run the second poll, but I can run that now. So we have that information. Would you like the results of the first poll first?
Yes, please.
It was 52% said yes. And the question was, I don't know if it'll let me wind up to the question, I apologize. 29% absolutely, 12% said, what's that? And I think that's a reliability system. And 8% said, we may still have some tools in a cabinet somewhere. So if you'd like, I can wrap us up by running the final poll, which was, does your organization have a root cause failure analysis team?
Yeah, that'd be great. And I was just kind of curious as to who my audience was today. So that's what the purpose of that first poll was. And so, yeah, if you have any questions, any comments or concerns, I believe in the next slide, there's my information. And I probably just kicked Robin out again with that last poll. I'm sorry.
No, it's all good. The poll's up. I think it closes in a second. Just let everyone have a chance to vote on that one. Cool. I think we've got quite a few still coming in. 64% of people voted. Awesome. On that one, oh, there we go. You can see you should be able to see the answers there now, Taylor.
Should and is are two different things.
That's okay. So I can let you know them. So 52% said our organization has an RCFA team. 34% said we just keep fixing the same stuff over and over. 13% said we use an outside service, and 1% said nothing ever fails in our organization.
Well, I wish I worked there. So I'm pleased to hear that so many people, so many organizations are using an RCFA process. And for those of you who aren't, try it out. I mean, get some people together. Get your vibration data to collect together. Get your maintenance leaders together. Get your operational leaders together, and have some discussions and ask the whys, and see if you can't figure out why you're experiencing those failures. And if you get to the root cause, you may just be able to rule out what that problem is. And maybe I will have done you a favor today.
Awesome. Thank you so much, and thanks to everyone who joined us today. There will be a brief survey that will pop up, which is just 6 quick questions just when you log out. If you'd be so kind as to take the time to respond to that, we do really appreciate it. And it helps us to improve these webinars each and every time that we take them. If you have any other questions, or if you'd like to connect directly with our team, you can either reach out to Taylor, whose contact details are on the screen, or reach out via our website or on LinkedIn. Thank you so much for all of your time, and have a lovely rest of your day, everyone. And thanks so much again, Taylor.
Thank you.
Thanks. Bye-bye.